So our first question, you don't even need the gizmo, it's just prior knowledge. So what you already know about distance and speed and things like that. So Max ran 50 meters in 10 seconds. Molly ran 30 meters in 5 seconds. So who ran farther? Max. Max ran farther. Okay, but who ran faster? Molly ran faster. Okay, so Max ran 50 meters in 10 seconds, and Molly ran 30 meters in 5 seconds. So we can figure out their speed by doing distance divided by time. So for Max, he ran 50 meters in 10 seconds, so that's going to be 5 meters per second. Okay, and Molly, even though she only ran 30 meters, she did it in 5 seconds. So that's going to be 6 meters per second. For the gizmo, distance is on the y, time is on the x, it's meters per second. Okay, so you had to make your graph look like this and then answer some questions based on the runner in this graph and hit play on that. So what did we observe? I have 2 check marks for this one. Yep, he's running to the right. So he's running away from 0, constant speed. Okay, we have a straight line, it's not a curved line. And even watching the runner, you can tell he stayed at the same speed the whole time he was running. So constant speed. What is the runner's position at 1 second? 10 meters. So if we go up here, at 1 second, our graph is at 10 meters. Okay. What are the coordinates on the graph for that position? 110. Okay. Your x is 1 and your y is 10. 110 for that point on the graph. Okay. Then they ask, when was the runner at 30 meters? So 30 meters, we would read that here on the y. So yep, and then we go over, and that's going to be 3 seconds, exactly. So at 3 seconds is when he was at the 30-meter line. And what are the coordinates for that one? 330. Okay. It's going down here. So I have 3 check marks. It says, look at the graph to the right. Notice where the green line is. If you could see the runner and the stopwatch at this moment, what would you see? Reset, play. So that's what our runner looked like. Okay, so what did we see for this line? I have 3 things checked. Yes, good. So they're going back to 0, back to start, negative direction. Slowly, yes, slowly. So do you see how the line is a straight line and not a curved line? So that means they're going to be running at a constant speed. But see how it's it's almost a flat line. It's definitely not as steep as the line we were looking at last time. Okay, because it's a flatter line, he's going to be going slow. But he is going to be going at a constant speed. So that's the other check mark that I have. So I have towards start, negative direction, constant speed, and slowly. What is the runner's starting position? This is tricky because it's kind of hard to see because the dot's big and it's kind of pixelated. But if you count each line, they go up by 2s. So I got 23 meters. Because to me, it looked like it's in between those 2. It's like not on exactly one of those lines. So I put 23 meters. But you can tell where it is on the y-axis. That's the starting point. Okay. And then where did he end up? And then on this one, I got 15. Because if you go by 2, so this is 10, there's 12, there's 14, and there's 16, and it's kind of in between those 2. So that's how I got 15. Okay? So what does the y-intercept tell us? The y-intercept is where the graph hits on the y-axis, right at time 0. So if we're looking at this point here, that's for example, that's a y-intercept. What does that tell us? The starting position. There we go. Starting position. So the y-intercept will tell us where the runner or the object is starting. All right, it says in the gizmo, set the number of points to 3, then create a graph of a runner who starts at the 20-meter line, runs to the 40-meter line, and finishes at the 30-meter line. Okay, so starting at the 20-meter line, that's going to be your y-intercept. So 20 meters, your graph should have started there. And then if your graph had 3 points, then your next point would have been at 2 seconds in the middle of the graph, and that said that you needed to go to 40 meters. So you should have a point there up at 2:40, 2:40. And then it says you finish at 30 meters. So at 4 seconds, you should be at 30 meters. So up and then down. So what's the y-intercept of your graph? Where did we start? We were at 20 meters at 0 seconds. For the next part, we were looking at the direction of the runner. So for number 1, activity B number 1, they wanted to know, what does a graph look like if your runner is going away from the starting position? Does your line go up or down? So the line is going to go up, which is, it means it has a positive slope. Right? Positive slope. You're going to run in the positive direction, to the right. So if a runner is going back towards the start, back to 0, what does that look like? What are your line? Your line should go the opposite way, right? It should go down. So line goes down, which would be a negative slope. Number 3, so set your number of points to 5. Create a graph of a runner that runs left to right. So they're running to the right for 1 second. If we're running to the right, is our line going up or down? Is the right positive direction or the negative direction? Positive, right? So we want our line to go up. So you're going to have a line that goes up for a second. Then they say rests for 2 seconds. For resting, you're stopped. So what's the line going to look like if it's stopped? Flat, very good. So you need a flat line for 2 seconds. So it needs to cover 2 seconds there for your flat line. And then it says, then continues running in the same direction. So for the last second, we're going to keep going with an up line. So something like that. Up, flat, up. So it doesn't really matter what your graph looks like, but it should go up, flat, and then up again. So how does the graph show a runner at rest again? Flat, horizontal, slope equals 0. In general, how does a distance time graph show you which direction the runner is moving? So if your slope is going up, you're running to the right. If your slope is going down, you're running to the left. So for this graph, where does the runner start? 0 meters at 0 seconds. So that's where we're starting. At 2 seconds, where is the runner? How far has he gone? He's gone 10 meters. So here's 2 seconds. Go up 10 meters after 2 seconds. Where will he be after 4 seconds?
40.
At the 40. So 4 seconds. Can you go up? There you go. Over 40 meters. Find the distance. Okay. What do you notice about the first half of the graph compared to the second half of the graph? In which time interval do you think the runner was moving most quickly? 2 to 4, right. And how would you know that? What about the graph, what about the line tells us that he's moving faster there? So what about this line tells us he's moving faster than this line? So because this line's steeper, we know that he was moving faster. So let's actually calculate that. Let's calculate the speed. So remember guys, the speed, we've talked about how the speed is the same as the slope. And slope, which you can find by doing, bless you, rise over run. Okay? So for the 0 to 2 seconds interval, what's our rise? So 10, he goes up 10, and then over how many? 2. So 10 divided by 2. So yeah, that's going to give us a slope or a speed of 5 meters per second. And then for the second interval, from 2 to 4 seconds, so from the 10 to the 40 is our rise. How far is that from 10 to 40? 30. So that's our rise. And then how many seconds is it from 2 to 4? 2 seconds. So what's 30 divided by 2? 15. Okay, so that is just proving our point, right? Steeper slope is a faster speed. So 2 to 4 seconds, we were going 15 meters per second, which is much faster than the 0 to 2 second interval where we were only going 5 meters per second. In general, how can you estimate the speed? Good, steepness. 8 and 9 we talked about in class. For a runner that is speeding up, moving away from start, what does that look like? Is it curving up or does it start to flatten out? It's going to get steeper, right? So it's going to curve up. So the line gets steeper as you go. Now, if you're slowing down, still moving in the positive direction, you're going to start off really steep and then you want to get flatter as you go. So you're still going in the positive direction. It's going up, but it's getting flatter, which means you're starting to slow down. So you're still accelerating, but it's a different kind of acceleration. So this one would be positive acceleration. And this one would be a negative acceleration. Look at the image below. So we don't really even need the gizmo for this one. We're just looking at a snapshot of the runner, okay? What can we tell just by looking at this snapshot? All we can tell from this is the direction of the runner, okay? Is the direction positive or negative? Positive, it's to the right. So is the line going to be going up or down? Positive is up, right? So all we can tell is that the line is going to have a positive slope. It's going to be going up. What is not known about the graph looking at the picture? Starting and ending position. So look at the time here. Is the time 0? No. So we know that that's not the starting position. We don't know where the starting position was. Right? We don't know where that was. And we know that this is a snapshot. This is the middle of the run, so we don't know where he ended either. Good. We don't know if he's running at the same rate or if he's speeding up or slowing down. We don't have the graph to have that information. We're only looking at a single point on the graph. Steepness of slope. We don't know if he's going fast or slow. So, activity C. Now there's nothing to write down for the first one. They just wanted you to play around and make each of those scenarios happen. So based on your experiments, answer the following questions. How does the graph show if a runner gets a head start? So let's start that. All right, so what's happening at the beginning of the run with the blue runner? Where does the blue runner start? 10 meters, and then the red runner is starting at the 0. So who has a head start here? Blue. Blue has a head start. Look at the graph. So looking at the graph right here, what does that look like? What does a head start look like? Do they start at the same y-intercept? No. So they're going to have a different y-intercept. That's how we know if one runner gets a head start. You get a different y-intercept. Just abbreviated that. How does the graph show which runner is going faster? Which runner was going faster there? Red's going faster, right? Because by the time that they get to 4 seconds, by the time they've been running for 4 seconds, what happened to that head start? It's gone, right? Red runner is caught up to blue runner. So if they're going to catch up, they must have been running faster. What can we say about the red line compared to the blue line? Steeper. There we go. So the steeper line is going to be the runner that's going faster. So steeper slope, faster runner. Next question, how does the graph show which runner wins the race? So let's say that, they're racing to the 30-yard line or 30-meter line. Blue gets to the 30-meter line there, but red doesn't get to the 30-meter line until 4 seconds. So blue would win the race at a little over 2.5 seconds. And red would lose. They didn't get there till 4 seconds, so they were behind. The wording, this one is a little bit weird, so I'll help you with this one. I just said that the runner reaches the distance in a shorter time. Let me do a different scenario. So now the lines are crossing. What happens where they intersect? What's happening? Passing, yes. So when the two lines cross each other, that means that one of the objects or the runners is going to be passing the other object or runner. So whoever has the steeper slope is passing the other runner. So a dog is chasing a cat towards a tree. I'm just going to zoom in here and draw the graph. The cat has a 10-meter lead and runs at a speed of 6 meters per second. The dog runs at a speed of 8 meters per second. The tree is 30 meters away from the dog's starting position. Which animal will reach the tree first? Okay, so if the dog starts at 0, the dog can run 8 meters per second. That's the slope. So that means you're going to count up 8 meters and over 1 second. Okay? Oh, up 8 and over 1. So it goes by 2. So go up 4 squares and over a second. So there. And you just keep doing that until you get all the way to 4 seconds. Okay, so there's the dog. Okay? The cat gets a 10-meter lead. So where's the cat going to start? If the dog's at 0, the cat's going to start at 10. Okay? But the cat can only run 6 meters per second. So the cat's going a little bit slower. So up 6 over 1. Who is going to reach 30 meters first? Do the lines ever cross? Nope. So the dog really never catches up to the cat, does it? Because the lines don't cross. So here's 30 meters. Cat gets there first. Dog doesn't get there until like a half a second later. So a police officer is chasing a purse snatcher down a street. The thief starts 9 meters ahead of the police officer and can run 20 meters in 4 seconds. So let's say if the police officer starts at 0, our purse snatcher is going to start at 9. Our purse snatcher can run, what did we just say? 20 meters in 4 seconds. So after 4 seconds, if he starts at 9, he's going to be at 29. Okay, so right there. So connect your dots. There we go. Police officer can go 32 meters in 4 seconds. So 32 will be right there because they go by 2s. Okay? And where they intersect is where the police officer will catch up to our purse snatcher. Okay? So it's about 3 seconds, maybe a little bit after 3 seconds. So close to 3 seconds. Okay, if you look and you go down, it's about 3 seconds. In a football game, one team kicks off to the other, okay? And then they're talking about a receiver and a tackler. So the receiver and the tackler, they're going to be running opposite directions, right? They're going to be running at each other. So that means one of our lines is going to go up and the other line is going to go down. We have to read carefully to figure out which one goes up and which one goes down. Okay? It says that the receiver is going to run left to right. So our receiver is the one running in the positive direction, okay? So our receiver's line should go up, and our tackler is running right to left, so he's going to run in the negative direction. So his line, the tackler's line, goes down. It says that they start 40 meters apart. So somebody's going to start at 0, and somebody's going to start at 40. Okay? Our receiver is going to run, he can run 10 meters per second. So let's make this our receiver. So that means 10 meters per second. So after 44 seconds, he's made it 40 meters. Okay. Up 10 over 1. But our tackler, he's a little slower. Okay. He's probably a bigger dude. So he runs 6 meters per second, but he's going backwards. So he's going to go down 6 meters over 1 second. All right, so there's our tackler. So how far did our receiver get before our tackler got him? So if we're looking for how far, then we need to look over here. How far is that? It's right in between 20 and 30. 25-yard return, or 25-meter return, sorry. And how long did it take to get caught? Okay, about 2.5 seconds. Classic story, Tortoise and the Hare. Tortoise challenged the hare to a 4-hour race. The hare is so confident of winning that he allows the tortoise a 10 kilometers lead. So now we've switched to kilometers per hour. So the tortoise is going to start here, and the hare will start at 0. The hare runs at a speed of 14 kilometers per hour, but stops for a 2-hour nap in the middle of the race. So we need to go up to 14, but he's going to stop in the middle. Okay, and then it says he wakes up and goes, well, it says they took a 2-hour nap in the middle of the race. So we're just going to assume that he woke up and went another 14 kilometers. Plods along at 4 kilometers per hour for the whole race. So he's going to go 16 kilometers in 4 hours, but he started at the 10, so he's going to go 26 kilometers. All right. So in the classic story, who wins the race? Usually. Tortoise. Oh, but in this situation, who won the race? The hare. So the hare finished just 2 kilometers ahead of the tortoise here in our situation.